you have in your hand, and you can make notes and you can do the calculations that I'm save the calculations in your notes. But I'm also going to write on the slides, so the answer will be on here too. So this section is about charge and current, and what is charge and current, and ultimately what is voltage and power as well. So we have to go back and do a little bit of a chemistry review and recall that an atom is like the solar system. It has a center and it has something that goes in circulates or orbits around the center. So the center contains protons and neutrons. Protons have positive charge, and electrons have negative charge. Electrons are circling. So in this picture, so it wanted to switch me. Let me switch here. In this picture, the electrons are circling, and this is the nucleus of the atom, which has positive charges and neutral charges. And my cartoon is self-explanatory about what who's positive, who's negative, and who's neutral. So the way you tell the total charge on an atom is by counting up the positive charges that are in the center and the negative charges, or the electrons, that are orbiting the nucleus. So a simple atom, a hydrogen atom, has one proton in the middle and one electron. So one positive charge plus one negative charge is a neutral atom, right? Similarly, this is helium. It has two in the middle, two positive in the middle, two on negatives. If it has a charge, overall charge, it is an ion. But some of the small atoms have special names as well. But anyway, so here's copper. Copper is a conductor. Wires are made out of copper. So let's see what's happening in copper. Copper is atomic number 29, which on the periodic table, which is on the next chart, means it has 29 protons in the middle, and when it's neutral, it has 29 electrons orbiting the outside. And the electrons have to be in certain layers. It's like only 2 electrons can be in this center orbital, which is like Mercury, right, in our solar system. And then 8 can be on the next ring, and I forgot the number that can be on the next ring after that. And then you see this last orbital out here, to add up to 29, only has 1 electron in it. And because opposite charges attract each other, so this is a bunch of positive charges, and these are a bunch of negative charges, and they are attracting each other, but they're also going around, and around. But because you have this attraction going on, and this guy is the farthest away from this positive charge chunk in the middle here, this electron can actually escape pretty easily. And so that's what makes a good conductor, is having very few electrons in the outer shell. And when there's very few in the outer shell, these electrons can escape easily, and so that makes a good conductor, because electricity is actually the flow of electrons. So this outermost shell is always called the valence shell, and how many electrons are in the valence shell is what determines whether this material is a good conductor or a good insulator. So insulators have many electrons in the outer shell, and so there's lots of negative charges out here being attracted to lots of positive charges in here, and the negative charges out here are held in pretty tightly. It's more balanced in a way, you could say. So that makes a good insulator. So this is the periodic table of elements that you guys have probably seen in your chemistry class somewhere. The metals, transition metals, are all these pink ones right here, but you see there's copper, number 29, there's nickel, cobalt, zinc, this is gold, this is silver, this is gold, platinum. So these are all conductors, right? And you will find out that they all have very few, or maybe only 1 electron in their valence shell. Our semiconductors, which we'll talk about later in the semester, tend to be over here, like the silicon, the gallium, germanium. These are all things that you make integrated circuits out of. Okay, so charge. Officially, charge is an electrical property of atomic particles. So I showed you the hydrogen with 1 positive charge, 1 negative charge. It has no overall charge. Its net charge would be 0. If it had 2 electrons on it, its net charge would be -1. So charge is measured in coulombs, and 1 electron one electron has this much coulombs of charge. So that's a really, really tiny number. So when we talk about current, current is lots and lots of electrons. So it's actually more convenient to say a coulomb of charge is this many electrons. Where did we get that? It's because one electron has this many charge, this much charge. If I do the math, one electron, each electron has that much coulombs charge, and you do the math and you find out that there's 6.24 times 10 to the 18th electrons in a coulomb. It's a lot of electrons. But we don't want to talk about coulombs of charge going by. That would be, we don't want to talk about how many electrons are going by. We want to talk about how much coulombs is moving in a conductor. So, ITRO people, please note that there's a mistake in your book on page 29. It says that this is 6.25 times 10 to the 18th. And even if I invert that number and do the calculation, this is the answer that I will, or invert this number and do the calculation and extend it to more significant digits, it'll not be 6.25. So your textbook has a mistake in it. It's 6.24. If you're good, even if you're rounding off, the answer is 6.24 times 10 to the 18th electrons in a coulomb of charge, in 1 coulomb of charge. So here's kind of an illustration of it. Current now is defined as the flow of charges. So I don't want to talk about the flow of 10 to the 24th charges per second. I would rather talk about the flow in coulombs per second. So big chunks of charge per second. So current is actually defined as a coulomb of 1 amp of current is 1 coulomb of charge passing by in a second. So here's my exaggerated picture of a wire. The electrons are moving in the wire. And when 6.24 times 10 to the 18th electrons pass by this plane per second, then I have 1 amp of current. So that's the definition of 1 amp per current. All of these 1 amp of current is 6.24 times 10 to the 18th electrons per second passing through this point in the conductor.
So it has nothing to do with how big the wire is, like the area of the wire, it's just how much current is passing by.
An amp is a rate of electrons per second passing by. So if you have a big conductor, technically you could carry more current, right? But without the wire burning up. And a small conductor, because there's some heating that goes on, the electrons are bouncing around atom to atom. They're actually literally going from one copper atom to the next copper atom, jumping the shells in the shells because they move off easily. But if that's a vibration, an atomic vibration, and it will make the wire heat up. So if you try to put too much coulombs, too much current through a wire per second, the wire will get hot. So if you need to carry a larger capacity of current, you need a larger wire. So let's do an example, and I will note that your textbook at this point has an error in it. ITRO students, your textbook has an error in it. So how many coulombs of charge are there in this giant number of electrons? So I said when you do your homework problems that you need to, 1, write down what you know. So what do I know about this problem? Now I had this working really good. The number, I just tried this out yesterday. Try again. The number of electrons, and I write it down because this helps me to sink in what's happening on this problem. 93.8 times 10 to the 16th electrons. What else do I know about this problem? I know relationships. So I said when you're doing problems, you write down the relationships. We know that there's 1.602 times 10 to the minus 16th coulombs in 1 electron. That's how much charge there is in 1 electron. So I have electrons, I have coulombs per electrons. Even if I just look at the units, coulombs per electron times electrons would give me an answer in coulombs. So that's exactly actually what I'm going to do. I'm going to say I have 93.8 times 10 to the 16th electrons. and then I have 1.602 times 10 to the minus 19th coulombs in one electron. And then I see that electrons cancel out. I will get an answer that is in coulombs. And somebody want to calculate that?
0.150.
Yep, I agree. 0.150 coulombs. So
366, right? Because the electron only has 3.
that's correct. And so it's proper to put down the 0 there. Yeah. 3 significant digits. And
I have a question.
yeah,
How did the 16 become, how did it become 19?
because I did my dyslexic thing there. Thank you. So, and then properly in your homework, you would box the answer in, make sure units are on there, and then that would be proper in your homework. Okay, not too bad. Next example. 10 coulombs of charge flow past a given point or cross-section of a wire in 2 seconds. What is the current? So I know I equals Q divided by T. I know I have Q equals 10 coulombs. T equals 2 seconds. So I wrote down what I know. I wrote down relationships that I know. Maybe I write down other things. Maybe I'll use it. Maybe I don't. But G, I have a relationship. I want to know what I is. And so not too bad. I equals 10 coulombs divided by 2 seconds, which equals 5 coulombs per second. What's the definition of an amp? An amp is defined as, and that little symbol means is defined as, an amp is defined as a coulomb per second. So that does equal 5 amps. Circle my box in my answer. Okay? All good? Okay, so a moment of notation. This will affect both classes, although, well, let me just tell you what it is. A moment of notation. When I have a capital I like that for current, that means DC, or not varying with time current. If I have a little I, and it will often be written I as a function of time, that's something that changes with time. So that would be an AC current. In the ITRO class, we don't really use the lowercase letters till mid-semester. The EE class doesn't care and uses I as a function of t right from the start. But notation-wise, a capital I is not time varying, and a small I is time varying. Same thing with charge. This is either a total charge or a DC charge, you could say, a charge that's constant, not changing with time. And a little q of t. I notice the EE book just writes little q, and they imply that it's a function of time, but it's really a function of time, would be something that's time varying. So it changes with time. So this capital versus small case notation will apply to current as well. I mean current, voltage, charge, all of those things. My handwriting isn't really this messy. It's this electronic pen makes me messy. Okay, so here's examples for the EE students. See what. Pull my notes out. So this will be something that will be similar to what you have in your homework. So here's my first example. Q of t, you're given charge. Let's say it's 5t squared plus 3 coulombs. And I want to find what is the current. So in this case, you're going to use the relationship that current is the time rate of change of charge. So current is kind of like, in a way it's like the velocity of the electrons, because velocity is a distance, only this time it's a charge, over time, right? So you could actually say I as a function of time is the change in charge over a certain time period. So anyway, this is a derivative out of calculus. Calc 1, I guess, is where you do derivatives. So I of t equals the derivative with respect to time of 5t squared plus 3. Remember how to do the derivative?
10t.
Yep, 10t, and derivative of that is 0. So my answer in the end, I of t equals 10t.
And then you just plug in t for seconds, and that'll tell you what the current is at any given time.
Yes, it'll be an instantaneous current at any given time. Because what is current? It's an instantaneous rate of charge passing through a point, right? So it's a rate of charge passing through a point. So I at time, in this case, I at time 3 would be 30. Since I'm in coulombs, so this is coulombs, this is second, so my answer would be in coulombs per second, which is 30 amps.
And that's for alternating current, but for direct current, would it just be like the same over time?
So a direct current example would be something like saying Q of t is 3t, right? And then when I do the derivative, d dt of Q of t, I would get the answer is 3. So that would be something like a DC current. Okay. An AC current, derivative of sine is a cosine, right? And so the trickiest that your homework gets will ask you to use the chain rule. There is a problem, something like gives you that Q of t is, I'll just make something up, e to the minus 2t sine 10t. It'll give you something like that, coulombs. So you have to use the chain rule to do this one. This, by the way, is a realistic problem. This is a problem where the charge is doing something like this. That's what the charge is doing. And it turns out the current is doing something similar. So derivative with respect to time of Q is d dt of, I like to be thorough, I always write my problems out, which is, by chain rule, it's derivative of the first times the second plus derivative of the second times the first. Product rule, yeah. That's also called, yeah, I called it chain rule. But, okay. Chain rule, product rule, isn't that the same thing?
No, chain rule is like if it's sine of 10t, chain rule would say
Oh, plus the derivative of the thing inside. Yeah, sorry. Okay, yeah. So derivative of the first is minus 2, because you have to take the derivative of this. This is your chain rule in action, right? E to the minus 2t. Derivative of the first times the second plus derivative of the second, which, so I have to take the derivative of what's in here first. It's 10 sine, it's 10, and then times the derivative of the sine, which is the cosine, 10t times the first, e to the minus 2t. So that's the answer. E to the minus 2, e to the minus 2t sine 10t plus 10 e to the minus 2t cosine 10t. That's the answer. Oops. I can't draw a straight line on this board. Okay, so you have homework problem like that where you have to do a product rule type of derivative. And that's what I of t equals. Okay. EE students, gives you this formula of Q with a big Q equals the integral of the current. So since remember that I of t is dq dt, I integrate both sides. Actually, no, I don't do that. I do I dt equals dq before I can integrate both sides. And then you can get this relationship here. So one of the things I wanted to point out different is that your homework problem often asks for a q of t. If it's a capital Q, you're integrating between two known values. If you're asking for what the charge is as a function of time, you need some initial conditions and you do the integral without the boundaries. So here's my example. Do I have an example here? So let's say that you are given that I of t equals 5t. And you're given initial conditions of t at time 0 equals, I don't know, let's make it equal 1. So I want to find what q of t is. So I need to integrate I of t dt, which is the integral of 5t dt. So if I integrate that, it becomes t squared, 2 goes into the denominator, 5, and plus a constant of integration, an unknown. So I use my initial conditions over here to figure out what that constant of integration is. And so I said t, somebody caught me, q at time 0 is 1, is my initial conditions. That's time. So q at time 0 equals 5 over 2, 0 squared plus some constant of integration. We know q at time 0 equals 1. 1 equals 0 plus the constant of integration. So my constant of integration is 1. That means therefore. So finally I can get that q as a function of time equals 5 over 2 t squared plus 1. So there's your final answer in coulombs if I was given in amps. So not to take all the ETRO student time, I will do in the lab, you have a problem in your homework where they give you that I of t is of the form e to the t sine or cosine, sine or cosine something t. So you have to integrate this. Do you guys remember how to integrate that? Yep. And I will do that on the board in the other room for you guys if you need a refresher on that. Okay. So I said that opposite charges attract each other, like charges repel each other. This is important for how current is generated in a circuit. Of course, this is probably pretty straightforward to people, but it's like magnetism, right? The north and south pole attract each other, but south poles repel each other. But in circuits, why that becomes significant is when I had a piece of copper wire, the electrons can move around there freely. They move around easily from copper atom to copper atom, but they have no flow. There's nothing pushing them around and causing a current flow. A magnetic field will cause a current flow. If I move the conductor in a magnetic field, it'll push the electrons around, and that's actually the basis of generating AC power, which we'll talk about later. But you need something to push those electrons around and cause a current to flow. So that push is actually called an electromotive force. But in a circuit, if I have a battery, here's a battery, plus side, minus side, and I have a circuit, and I have some circuit element right there. I don't care what it is right now. It can be a resistor, it can be anything. And this is copper wire right here. And so there's a bunch of electrons sitting here in this copper wire. But if this battery wasn't here, these electrons wouldn't flow through this component and nothing would be happening. So you need some kind of a force to push them around. So notice on the battery right here, you have a negative side, a chunk of negative charges sitting over here, a bunch of electrons maybe, and you have a positive side. The positive side is really an absence of electrons. There's not enough electrons over here. So I have a bunch of electrons over here, and I have a nice pathway right here, and I have a place over here that needs a bunch of electrons because it's missing electrons right here, so it's all positive. So this battery here with this charge difference occurring right there will actually cause the electrons that come out from here and be attracted to the place where they're needed over here. So this is what causes the flow of electrons in a circuit. It has to be a complete circuit. It has to be a complete loop. I mean, if I have something like I have a circuit element here, and it's hanging out here in the open. This battery, plus side, minus side, this battery doesn't push electrons to dump out into the air like that. It doesn't work that way. There's no flow at all. This is a stop. So you cannot have electron flow unless you complete the circuit and make a whole loop right there. So voltage is this force that can push electrons around in a circuit and make current. This force is called an electromotive force, EMF. You will see EMF, especially in some older literature, or when you deal a lot of times in the AC world, they'll say so many volts EMF, electromotive force. More commonly we say voltage, or we also say a potential difference. The reason we call it a potential difference is because there is a difference right here. There's a potential to do work, to cause work to occur in the circuit. So 1 volt, which is a potential difference, exists between 2 points, like ends of a battery, when it takes 1 joule of energy to move 1 coulomb of charge between the 2 points. That is the definition. Bit wordy, but that is the definition of what a volt is. So a volt technically is energy to move charge, so a certain amount of energy to move a certain amount of charge. Energy is in joules, charges in coulombs that we already know. So here's my example. If it takes 50 joules of energy to move 10 coulombs of charge, then the voltage is 5 volts, because voltage is energy, 50 joules, divided by 10 coulombs. So that's 5 joules per coulomb, which equals 5 volts. So 5 volts potential difference exists wherever this charge difference is sitting in a circuit. Could be like a 5-volt battery. Here's my battery drawing, and here's the symbol for a battery schematically. This is a battery with more than one big and little line, as opposed to a cell. A cell is written like that. It's interesting, if you open up a 9-volt battery, you will find out that a 9-volt battery is composed of 4, 1.5, 3, well, more than 4, okay. A 9-volt battery is composed of cells put together, 1.5-volt cells. So this is a cell, this is a battery. Sometimes they're used and mixed up erroneously in the literature. Here's the inside of what a battery, an alkaline battery, looks like. It's a chemical reaction that occurs, an electrolysis process that causes electrons to be at one end and absence of electrons to be at the other end. There's a really nice link here if you want to learn all about batteries. So electronics makes a distinction between active and passive circuits, circuit elements I should say. Passive circuit elements do not produce any electricity. They don't amplify anything. Passive elements are things like resistors, capacitors, inductors, relays, transformers. Those are all passive components. There is not more power on the output side than there is on the input side. They consume power. These things consume power. Next week you will start resistors. Resistors limit or resist the flow of current, so it will limit how many electrons can go through it. But in the process of limiting how many electrons can go through a resistor, the carbon atoms shake around and generate heat. So heat is given off by the resistors and they consume power. Active elements are things that produce electricity. So you can technically say a battery is an active element, but also op amps are considered active elements. So more power comes out of an op amp than goes into an op amp, and we'll learn why that works. The EE textbook makes a further distinction that active elements and sources can be independent or dependent. So dependent means the output current or output voltage somehow depends on something that's happening on the input side. That's what it means. These are symbols that we are going to be using from here and forevermore. We will start with resistors next week, big time resistors, but these are the common symbols that we will be using. There's a couple of, here's source symbols. So constant voltage can also be written, you'll see it in the literature like this. Sometimes a constant DC source is also written like this. I actually do this quite a bit. This is a constant DC source. Doesn't say that can be a power supply, that can be anything, but it's a constant DC source giving you a constant voltage. This specifically is a battery, which is also a DC source. This is a source that's giving you current instead of voltage, and this universally is a symbol for an AC source. And then I do make a distinction between a cell and a battery. In our schematics and in the lab, you will see symbols for earth ground, chassis ground, and signal ground. Earth ground is literally a connection to the earth. This is our zero reference place because we live on earth. The voltage at earth is considered our zero reference place. It's ground. It is literally a tie point to the earth. Chassis ground. Chassis ground is this metal case surrounding this oscilloscope. So inside, there's circuits inside this instrument. This circuit cards inside this instrument have some physical wire tied to this outside metallic housing, or sometimes it's an inside frame. That's called a chassis ground. So an assembly drawing might have a symbol that says tie the circuit right now to a chassis ground. Chassis ground and earth ground are very often tied together. All our instruments have a chassis ground and earth ground tied together. Lastly, a signal ground is something internal on a circuit, and it doesn't necessarily have anything to do with earth ground. It's kind of a reference point in the circuit. Some voltages are above that point, some voltages are below that point.
Should we know like all of those?
You will see all of those in engineering world, and sometimes they're misused. Yeah, we will mostly have earth ground because we tie all our circuits to earth ground for safety. So, but you could in schematic see a chassis or a signal ground too. So I would be remiss if I didn't expose you to it.
Not just the grounds, but should we know all?
You will know all of them. You don't have to memorize them all right now, but as the semester progresses, you will know all of them. So energy and power. Joules are units of energy. Watts are units of power. So a watt is a joule per second. So when you look at your electric bill at home, you get electric bill, you get charged for kilowatt hours, correct? So what does kilowatt hours mean? So I showed you, so this is what you get charged for. It is a rate, it is an energy that you consumed. It's not actually, they call it the power bill, but it's actually the energy that you consumed. So a kilowatt is a kilojoule per hour. A kilowatt is, a watt is a joule per second, but there's no reason why it can't be a joules per hour, right? It's still joules per time. So kilowatt means that let's say I'm consuming so many kilojoules per hour, and then I have my hours in a billing cycle, and what happens is I'm ending up with kilojoules. So a kilowatt hour is really a kilojoule. And since some of you looked at me funny when I did this, let me just prove to you. So I have kilojoules. Let's say I have kilojoules used in 10 seconds. Well, a second, there's 60 seconds in a minute, and a minute there's 60 minutes in an hour. And if I keep doing that conversion, my seconds canceled out, my minutes canceled out, and I'm left with 1 times 60 times 60 divided by 10 kilojoules per hour. So I did convert my kilojoules, which is a joule per second, I converted it into units of kilojoules per hour. So now I have kilojoules per hour, and I'm using this many kilojoules every hour, and I did it for 200 hours, which means my answer is in kilojoules, some number of kilojoules. But what did I really have? I had kilowatts times hours. So power company gives you a bill in kilowatt hours. And it's really the energy that you used, not the power that you used.
How much do you charge, you think?
Hmm?
How much do you charge, you think, per hour?
I don't know what we're using. What do they charge you? About 49 cents per kilowatt hour here. It's really high. So when I lived on the mainland, in Florida, it was 7 cents per kilowatt hour. Yeah, so that's how high electricity is here relative to mainland. Mainland, I read somewhere that the average on the mainland was 10 cents per kilowatt hour, but we pay 49 cents per kilowatt hour here. Yeah. So solar panels are worth it here because the cost of electricity is so high, but people on the mainland don't really care because electricity is cheap. You know, when I lived there, I didn't turn things off. I left my computer on 24/7. I had 2 refrigerators. But I don't do that here. I turn things off. I never shut my router down. I never shut my computers down. Everybody in my family had their own computer. Nobody ever shut it down. Yeah, big difference.